Okay, so today we're going to continue with on the risk management, decision making ideas. But also, I would like to state here, we are going to, uh, in a sense, we are already into the real risk management topics. So we had to go through the what is risk essentials, then decision making. This was the second part, and then the third part is actually we're officially it has not started yet. Risk management is a separate part of the presentation which we have not reached yet, but in reality, the conditional probabilities and the base theorem is in itself risk management tool on its own. So this is why I do believe that we are already in the risk management topic anyways. Okay, so conditional probabilities, and I'm going to start with, this time I'm going to play the game with you. I mean, I skipped most of the games, but this game I'm not going to skip. And you have probably heard of this one. Have you heard of let's make a deal, a Monte Carlo problem? Have you heard of it? No?
No.
Okay, so the game is, it's a TV show. I skipped most of the TV shows. For example, Deal or Not, you have heard probably. I have skipped several other TV shows that I use in my classes here, but this one is a famous one. This is why I'm going to input it. It is a standard. It is a standard case of. It's not a paradox. It seems like a paradox, but it's not. It's something else. Then when you figure this out, you might actually there is a lot of insights. So it's a TV show where the competitors. There were several competitors, as far as I understand, and the finalist, the final competitor, who is after whatever they have to do in the previous stages, there is only one left. He or she is presented with this type of a very simple problem. You have to. There are 3 doors. Behind one of these doors is the big prize, and behind the 3 other doors, the 2 other doors, there is how to say, there is nothing. Okay, they typically put a cutout of a goat, the animal goat, but I rather don't like to say this, because sometimes my students would say, "Oh, a goat is still an award. It's still something." The point is that there is one door where you actually have the price, and the other doors actually don't have any price. And oh, sorry, but anyways, and the question is, you basically choose your own door. You pick your own door. Then you as a participant. Then the TV host, the TV show host, Monty Ho, by the way, is his name, opens one of the doors. Let's say this one.
Mhm.
And gives you the chance to change your actually, first of all, he hears what is your choice, then opens the door. So let's say we have set door number 1. He opens another door, not the one that you have picked. So you're left with 2 doors unopened. And there is the question, the Monty Hall question is, would you stay with your own door, with whatever you choose, or would you switch to the other door? And and obviously when he opens this door, he doesn't open a door where the car is. It's not a random, but he chooses the door, one of the doors that is no award. Okay, so did you get the idea so far? So you pick one, let's say pick door number one. Then you state, okay, I picked door number one. Then Montijo, okay, the TV host would open one of the other two doors behind which there is nothing. And now the question is, do you still keep your first choice or do you switch? And by the way, yes, what would you be your decision here, Vitaly? And without the explanation first, I'm going to ask you the arguments afterwards. So
you must know, I am biased. I have seen the film 21 with Kevin Spacey.
okay, you're not biased. You're not biased. You just have seen the. Okay, let me start with Daniel. If you think that you can break it up, but anyway, Daniel, what would you do? Would you switch or would you keep? Turn on your microphone. Your microphone.
Daniel, muted.
Microphone.
Yeah, sorry.
Yeah.
I would keep my decision. I remember a TV show which was famous in the German TV in the 90s, and they always played that game. And as I can remember, the most of the people they got, they were not sure about their decision and switched. And then the first impression is always maybe the best or the safest.
All right, right. First of all, great input. I did not know that this game has been played in Germany as well. If you can figure out and find the name of the show, this would be mostly helpful. And I'm going to dig out some footage of it. That's great. Second of all, thank you for your argumentation. Now, Vitaly, what would you think?
I would change, if I remember correct, there are about 13.3% which we get gifted. So if we change, theoretically.
It's more than this, but anyway, yes.
Okay. Maybe in 16.
Okay, but it is really about decisions. And the decision here is there are several factors playing here. There is a mathematical explanation, and by the way, the mathematical explanations have puzzled several, not one, but several of the greatest mathematicians in the world. Mostly because, and I told you this on Thursday, mostly because the biggest mathematicians discount the probability theory as a mathematics, and they are not really specialists in it. Anyone who has studied to some extent probability theory, at least in a capacity of I don't know, in a major in mathematics or stuff, or probably some sort of engineering, they would always have they would have the tools to understand the problem. But anyway, so there is a mathematical solution. But before the mathematical solutions, there are these psychological aspects here again. One of the psychological aspects actually was pointed out very well by Daniel, is that it is your intuition. Why you have to change. It is whatever it is. There is no change in the situation, or there is no such a much change about the situation, stuff like this. And this is a valid argument, especially if you think about it. We have three doors. I choose random. What do I gain by changing? There is no way that I can gain something. This is one. And second of all, if you think about it, you remember that we do not like to lose, right? So it is what would happen if you have chosen correctly and you purposefully, because you were asked to do so, switch, right? This would be a lot more unpleasant to the loss-averse personality than if you choose one thing and then it turns out that it's not that one thing. So that you didn't do anything actively to run away from your luck, right? So these two things are really, really playing the psychological on the psychological side of the things. By the way, and I have a lot of videos from, for example, you remember this TV show Mythbusters?
Mhm.
Yeah, they actually did a whole episode of their show on the multi-hole problem, and they actually did two different experiments. One of the experiment was it just statistical check of the mathematics behind it, and it checked out, of course. But the other experiment, which was the first one, was with about 100 participants who were given the same problem and asked the same thing. And out of these 100, if I remember correctly, nobody switched. Okay, some of them actually won, some of them didn't, but nobody switched. And they most of the arguments were just the one that were said. So that is, first of all, psychological situation. Second of all, the mathematics of it. And I'm going to switch to uh, writing. So before we open any door, what are the probabilities of you having the reward behind each of the doors? What are the probabilities here? 3 doors,
1/3.
1/3. So it's going to be 1/3 here, 1/3 here, and 1/3 here. All right. And
Yep.
since we don't have any other information, we have all these doors are looking the same. There is no reason to choose one or another, to prefer one or another. This is a correct estimation of the probability. This is correct. Then what happens is that you state your own door. Let's say door number 1. It doesn't really matter, but this. So you state door number 1, and if you remember, this was 1/3. This used to be 1/3, and this used to be 1/3. This is how they used to be. Now this obviously becomes 0, right?
Yep.
No, we don't count this. But the question is, what happens to this and what happens to that? And if you are not familiar with any movies that they use this actually up until probably 2005, this was still a huge argument among the world mathematicians. So it was kind of a mystery of sorts. After that, it became an obvious but kind of neat trick to show to your friends, and they started using it in some sort of movies, some sort of programs and stuff like this. So right now, a lot of them have done. So if you have not seen this, or if you don't remember anything about probabilities, or what is your intuition, or if you listen to what is your intuition, you might think that, and you probably would be correct, you might think that this would become one half, and this would become 1/2, 50% of it. Because in the new situation, there is no third door, and you're left with one, and it's one out of 2, and you don't see why you change. It was 1 out of 3. Now it's 1 out of 2. You actually improved your chances, right? In reality, though, I'm going to show you what is the correct, the analysis that kind of clears the thing up. The reality is that this is not correct, and the reality is that beforehand, and actually I'm going to, I'm going to return back, and I'm going to state it up here. This was 1/3, and this is 2/3. So basically, it is 1/3. If this is your choice, it is 1/3 of the cases you win, and 2/3 of the cases you do not win. Right? This is how we are observing it. Yeah. And once and this is correct way put these thirds, there is nothing incorrect here. If we move here, it turns out that this is still 2/3 in general. Okay, I'm going to put it here. This is still 2/3, and this is still 1/3. But you know that for sure this is 0. The open door is already 0. So it turns out that there are, instead of on the last door, instead of having 1/3 of a probability, you actually end up with 2/3 of probabilities, because 2/3 are for the total of these two doors, and you have actually one of them is 0. You have eliminated it, so this means that the 2/3 are left over the door number 2 in this case. So it seems like a lot of anti-intuitive, and you would say, how come? I mean, there is no sane reason to do so. And I'm going to explain you the same reason afterwards, but let's finish with the mathematics here. So it turns out that you actually double your chance if you switch from 1/3 to 2/3. And yes, it is actually 33% gain, or actually doubling your chances. This does not still give you the guarantee that you're going to win, but it still improves it, and I'm going to explain a little bit later why. So here is the same situation. So we have door number 1, door number 2, door number 3, 1/3, 1/3, 1/3. And you decide to, I don't know, you decide to, if your door was door number 1, and okay, and let's see, yes. So imagine that you have decided to go for door number 1, and we know, or the host knows that your car is behind door number 1. So this is the car. Let me mark it somehow. Car, goat, and goat. So the things that I'm putting in red is what the host knows. So let's assume that you have started by choosing door number 1, which is the car. When you point this out, the host can open either door number 2 or door number 3. It doesn't matter which one, right? If you have started with door number 2, since there is gold behind it, the host cannot open the car, right? And there is only one other door that he can open is door number 3. There is no other ways. There is no other chance here. And if you start with the door number 3, it's the same thing, because there is a gold behind it. Host cannot open door number 1. Actually, he can only open door number 2. So for the last 2 cases, we have 1/3 of a chances of all chances are 1/3 and 1/3. And if you don't change, you're going to end up with a gold, with nothing. And if you change, you're going to end up with a car. Okay, this would be, let's say, circle it for change. Okay, so basically in 1/3 of the situations, in 1/3 of the cases, in 2/3 of the cases, if you switch, you're going to end up with a car. In the other case, which is door number 1, whichever door he shows you, this is all sum of 1/3. This is 1/3 of the cases. Door number 2, door number 3, the sum would be the same. And since you have started with the car, if you switch, you're going to end up with the gold, but you still have this edge of 2/3 of a chance to end up with a car if you switch, instead of 1/3 of a chance of to end with the gold. So how comes Well, it comes from the fact that while we are here, there is no new information. As soon as we point out our choice of doors and the host has to open one door, actually the information that is in his head is added to the situation. Because since he cannot open the car door, he has to change, he has to open a door with some sort of condition. I mean, and this condition is really the new information that we can see. So all of a sudden, we start with an unconditional probability. There is nothing for us to prefer one or another door. And as soon as there is a new action, and the new action actually, the opening of the door actually represent what the host knows. He has not said it, he has not pronounced it, but he actually has given additional information here. And because of this additional information, we have changed the probabilities. Our prior probabilities, the one that were unconditionals, have changed to so-called posterior probabilities, which are conditional on some new emerging information. And in reality, what has happened is that the knowledge, some of the knowledge of the head of the host has been emerged and has been put in front of you. And it's not that behind door number 3 there is a goat. It's not that one, but the knowledge that of the where is the car is at least conditionally or at least partially reviewed. So this is how it all started. Actually, this is how we started our class. It all started a long time ago, and it started with this guy, Thomas Bayes. Well, they say that it started with him. In reality, everybody is most probably, at least the researchers, most probably think that the real founder or I don't know, the real discoverer of the Bayes theorem is Laplace, the guy that we spoke about yesterday. And yes, the formula looks a little bit hairy, and we are not going to go too much about it, to think too much about it right now, because I have prepared a special, actually two movies. Do I have two movies? Yes, I have two movies, which we are going to play this time, which actually explain it in a very plain manner. And one of the movies is really starting from the three doors problem, and the other movie actually explains how to solve the Bayesian problem without ever using the Bayesian formula, but using it the philosophy. Anyway, the Bayesian formula is it takes your prior estimation. So there is something that is, if you remember, we were speaking about prior distribution and posterior distribution, or theoretical distribution and empirical distribution. So if we know some sort of a prior knowledge, theoretical knowledge about some situation, we can add some, we call this likelihood, but it is actually based on the new evidence what you have as a change, and then in the denominator we basically put part of the world. We estimate for which part of the distribution or for which part of the world this new likelihood and this prior are actually valid. And if we know these things, so we know some sort of a new information, we know the prior information, and we know we have an estimation of the size of the world or size of the system that we are trying to analyze, then we can calculate the posterior, which means the new probabilities that are going to be updated. And this is the principle of updating probabilities. Now, I'm not going to go into with the formula anymore, but I'm going to actually start a video. Let me check if I have the. This is not the one. Ooh, where is my video? Not this one. Up here it is. Hopefully. Was this one? No, sorry, it's not this one. Let me. Okay, and also I will have to share my sound. Just a second. Can you hear me now?
Yeah.
Okay. So I'm playing a video and I'm going to make some comments here and there. The video has a very particular example so that it actually explains what you have to what you really need to know. But the examples could be many different, and actually there is hardly any part of our everyday life that cannot be put as an example here. The only thing that I would like to ask you if it's not too loud. So, is this too loud?
It's okay.
Okay. So there is this guy who makes these short presentations that are very useful. And here it is.
Hello, David Harper of the Bionic Turtle with a brief tutorial on Bayes' theorem or Bayes' formula, a basic idea in probability that turns out to have profound implication in practice. To illustrate it, consider my friend here, the stick figure character, facing a decision among 3 doors. But first consider he has no prior information. He is unknowing. He is ignorant.
So the same problem that we just faced before anything else, there are three choices that our player has to choose.
This is an unconditional probability, really. Now add some prior information. Assume that he knows he comes into possession of some information to indicate that one door is more promising and another door is more dangerous.
Okay, this is a similar case to what we have, but in the case of Monty Hall, it is a lot more stricter. Here we can have just tiny bit of new information. Instead of saying this door is 0, and we can have something else. But anyways, it's a new information input into the system.
This addition of new information rationally should affect his judgment and his probabilities. So this is really what Bayes' theorem about. It's about the introduction of new information to adjust the probabilities. So mathematically,
this is the Bayes formula, the same thing that I just showed you. You can see that you will see that the letters that he is using are actually on his own choice. It doesn't. The letters are not so important. Probably the thing that you should know is that in probability theory, this separator actually is a separator for conditions. So the probability of this, given that has happened, or something like this.
It looks like this, where we say the probability of G given that U occurs is equal to this. So this right here is a conditional probability because we're interested in the probability that G will occur conditional on the fact that U has already occurred. And it equals this. In the numerator, we have a joint probability. See, the probability of G, if that occurs, it gets multiplied by the probability of U given that G occurs. So in fact, what we have here in the numerator is a joint probability that both U and G occur divided by the probability of U. Okay, but if that seemed confusing, I'll show you a graphic. And just remember, this is a conditional probability. What we're doing is we're adding new information Now that we know, if we know that U is going to occur, what is our new conditional probability that G will occur?
So there is some explanation about the formula, but you see that it is much easier than it seems.
The denominator breaks out into this following way, but I'll go to a graphic to show you how this works.
So we are going to use, and actually this is the best way to use, is to use the so-called decision trees. We've already mentioned them before, and they're very useful when we would like to analyze and to understand the base formula. So let's assume that we have a very simple situation here, and the situation actually monitors two different things. One is some sort of overview of the economy in the or the economic situation in the country, and another is price of a stock. And when we combine both of them, if you remember, if we combine different simple events with their own distributions, we actually change the outlook of the general event. And furthermore, this would be the case now because we're going to speak about condition, on what conditions and what sort of values and stuff like this.
Consider a very simple bimodal case where we're looking at a stock, and the stock is sensitive to the economy, and so the economy, we simplistically say, has a 70% chance of growing and a 30% chance of slowing. Now our stock is sensitive to the economy. If the economy grows, if we get here into this up state, then the stock has an 80% chance of going up next year and only a 20% chance of going down. On the other hand, if we start out here and go down, if the economy slows, then our stock has only a 30% chance of going up. So let's consider the terminology. This 80% chance is a conditional probability. It is the probability that the stock goes up, see right here, given or conditional on the economy growing. And it's 80%, and so that's a conditional probability because it's conditional here on this first state. Similarly, this is also a conditional probability, the probability that the stock goes down, given that conditional on the economy slows. In that case, 70%.
First of all, I would like to say that there could be many more options. This is the simplest possible, just binomial. Second of all, you can see that here is 100%, here is 100%, and here is 100%. So all the cases within this side of the universe, all the cases within this side of the universe, and all the cases within this side of the universe. And if you know these numbers, you can calculate what are the joint probabilities of each of these final branches of the decision tree.
Now, what is the joint probability? Notice this is a little different here. This is the joint probability of both economy growing and the stock going up. So if we sit out here, that refers to the odds of us ending up here in this node, which is the only node that represents both the economy growing and the stock going up. So that's a joint probability. And it's in fact equal to this, the conditional probability of U given G, which is right here, 80%, multiplied by the probability, the unconditional probability of the economy growing. That's the 70% here. So this math here, if that looks a little confusing at first glance, look at the graphic, it's just intuitive. If I start here, the probability of ending up here is I have to go through both this step and this step. 70% times 80% equals 56%. That's my chances of ending up here. Because this is a two-step binomial, I only have 4 outcomes at the end. They're going to need to sum to 100%. So the unconditional probability, imagine we're sitting out here in front before anything happens. What is the probability that the economy will grow? That's an unconditional probability on 70%. It doesn't depend on anything. Now I consider the Bayes formula question.
So the Bayes formula question is really the important part here. It is, what if I can observe one event one phenomenon, and I would like to make conclusions about another, and they of course they are connected. So what if I'm observing the stock and try to figure out what is going on with the economy? Okay.
What if I observe at the end of the year that the stock went up? What is the, knowing that, if I have that prior information, what is the probability that the economy in fact grew? See how that's the conditional question? Given that I observe the stock went up, that means it either went up here or here. What is now the conditional probability that the economy will grow? We know the unconditional probability is of the economy growing to 70% before the year, but after the year, if we have new information that the stock went up, this changes our perspective or the probability that the economy grew. And to get that, we can apply the Bayes theorem. So that formula right here. And so this piece right here, the conditional probability is 80%. This probability of the economy growing is right here. That's the 70%. And the probability of an up movement is the addition of these two nodes here.
Please do mind that we have included a state where the share is up, but the economy slows down, because this is in reality what we can observe, and this is in reality what we would like to figure out.
Here. So if I multiply that out, the application of the Bayes theorem ends up looking like this: the conditional probability that the economy grew, knowing that I observe the stock went up, equals this, and that turns out to be 86%. So notice I went from an unconditional probability where I had no prior information that the economy will grow of 70% to a conditional probability of 86%. In other words, if I observe that the stock went up, and because the stock is so dependent on the economy, I can now upwardly revise my probability that the economy grew. And that's the application of Bayes' formula. I hope that was helpful. Thank you.
All right. So, and I'm going to return to I'm going to reshare my screen. So, out of this really, kind of heavy formula, we actually created, it's much better to be understood using decision tree. And the decision tree basically, and I'm going to on purpose draw a little bit more complicated one, is basically observing what we could observe as we are analyzing unconditional probabilities, and then we analyze and we are observing some other or maybe more than one scenarios or factors. Let me draw it a little bit like this, and I'm going to draw it even further down, because I can go and have conditions of conditions and so on and so forth, right? So basically, we are going to analyze. This is what we're interested in, and these are the connected or joint events which influence the main event. This is how we go. So, okay, having said this, I'm still going to send you to show you another video, which video unfortunately is too close to home, too how to say, too relevant. Okay, so you can see the video right now. Okay, yes.
Mm-hmm.
Right, so let me see if it's loud enough. And yes, it is about a disease, and it is about testing about the disease. So here it is.
Now we have another problem with probability. This is a actually very good applied problem. So let's set up the problem. there's a disease out there, and we have estimates that 10% of the population have the disease. Now we have a test to determine if you have the disease. You can think of this as swine flu perhaps, except that I think a lot more than 10% have that. Our test to detect it is 92% accurate. So that means if you have the disease, it's going to notice that you have it 92% of the time. But it also has a 5% false alarm rate. Now,
a very relevant question about the tests that we are using. I'm not sure whether you have used it, but I have already passed 12 different on 12 different occasions. Have made myself COVID-19 test. And a very common misconception is that if there is a certain how to say accuracy rate, then for example 92% or 98%, this means that the test is correct. That if you're positive, this means that 98% you have the disease. And also a big misconception about the 5% false alarm rate or 2% false alarm rate. All those things have to be accounted for. And also another thing that you have to, okay, I'm going to do this again, I'll explain this again. So this is what we have as a premise, as a beginning of the problem. Now let's move on.
That means if you don't have the disease, 5% of the time.
Maybe you can pause for a second. Just for me to understand, the 5%, where do I find them? Do I find them in the 8% which are missing?
No. This is entirely different thing. So this is where actually it will be shown here, but since you have a question, I'm going to explain it. So we have false alarm means that, all right, first of all, what are the two possible outcomes of the test? It is that you're either ill or not, right?
Mm.
And then if you are, if the test shows you that you're ill, there is 5% chance that you're not. This is the false alarm. And if the test shows that you are not ill, there are 92% chance that you are not ill really. Okay? And you are going to see this actually in the decision tree, and I hope that I didn't mess with this explanation what is in the video. So I think it will be explained very well.
92% of the time. But it also has a 5% false alarm rate. Now, that means if you don't have the disease, 5% of the time it will say you have the disease. So we have two questions that we want to analyze. You test positive. What is the probability you have the disease?
Actually, you know what? I'm going to draw you the standard statistical matrix that they like to use. So it is basically a matrix, 2x2 matrix. In this case, one is reality.
Mm-hmm.
And the other is observations. So you hope that these two things are the same, but they are never the same. Or it could be model, result from a model. And let's say I'm going to just use 1 and 0. So there is a huge population of possible entities. I'm just using the general term. Some of them have the value of 1, some of them have the value of 0, and this is a real fact. But after our observation, studies, analysis, whatever, we could figure out some of the ones and some of the zeros. So the number of ones that we have figured out and they are correct, this means that we are correct. So let's put them, I don't know, there is some number here. So these would be correct. There are some zeros, okay, some second type of entities that we have correctly identified as zeros. So these diagonals, this diagonal here is not the problem. The problem is the ones that we think that they're ones and they're zeros. So this one, and the ones that we think are zeros, but they are ones. Okay, these are the real problems. And the ones that are here are typically said to be the so-called the first type of statistical error, and the ones that are here is the so-called second type of statistical error. But really, the false alarm will be here, 5%. Okay, in this case, it shouldn't be. It should be the other way around. So it's all right. It depends what ones and zero we put. But anyway, if we say one is non-capital and zero being a new one, ill person, then this is going to be 5%. So we think that this person is ill, but in reality he is not. And here that we think that this person is healthy, but he is not. This is actually, in your case, 88%, right? Did you get it right now?
Mhm.
Okay, so basically we have correct estimations in most majority of the cases, but we still have incorrect on some. The test doesn't give us the whole truth, and we might still end up making errors. Okay, I think this will be explained a little bit better here. Okay, so I'm going to return a little bit back.
And it will say you have the disease. So we have two questions that we want to analyze. You test positive. What is the probability you have the disease? In the other cases, your friend tests negative. What is the probability your friend actually has the disease despite his negative test? Now, this is a problem here. People get confused about a lot of the time. They say I tested positive. I should have it 92% of the time because the test is 92% accurate. And this kind of thing is it's a common misconception we're going to look at. You could talk about this with regards to lie detector tests, testing baggage at the airport to make sure no prohibited items like guns or knives are going on the airport. All these kind of things involve similar mathematics. The numbers may change, the populations may change. In this one, I didn't even tell you a number of people because you don't really need it. You simply need this number here. The 10% have it. So, and what we have here is a Bayesian probability, but we have to keep our terms very clear. There's two different things that are going on. You can really have the disease, so there's reality, you have the disease or you don't. And you can test as if you have the disease, test positive or test negative. So what we're trying to find is the probability that we'll call H for have the disease, given you test positive. So we know you tested positive. What is the probability you have the disease? And actually this is easy to calculate. There's a formula called Bayes' formula for this. And you can look it up, but we're not going to really need it. We're going to kind of go around the terminology to write Bayes' formula makes it look far worse than it really is. So here's what we're going to do. We're going to start off here and make a tree. And the tree starts with reality first. You either have the disease or you don't. So don't have it, block over H, so not having the disease. So what's the probability you have the disease? Well, 10%. Then obviously the probability you don't have the disease is 90%.
Okay, Vitaly, I think you got it so far. We have unconditional probabilities. If it's 10% for the general population, then this means that on average you have 10% of having the disease. You get it so far, right?
Yeah.
Okay. Now, the next thing that we're going to do is observe. So basically make our own test or make our own model, whatever it is. And this model will give us a little bit more information. We're going to introduce more information into the system and we'll see how the probabilities update.
Okay. Now, in either case, you can test two different ways. Positive, negative. Maybe should have made those a little further apart. So this is dealing with our test of the condition. So here's reality, here's our test. Now if you have the disease, you will test positive 92% of the time, 0.92. And now that gives us an obvious number here. If you test positive 92% of the time, you will test negative 8% of the time, or 0.08.
Okay, did you get it this one?
Mhm.
Right? So even disregard the first part. If you're looking just in the test, you're going to test positive and of course you're ill. We know that you're ill already. You should test possible at 92% of the time, and you should test negative 8% of the time, which basically means that our test is not accurate enough, right? This is what it is. And the same will go, the same similar we will think about if you're not having the disease.
And we can get these final probabilities by multiplying. 0.10 times 0.92 is 0.092, 0.008. Now here you don't have the disease. How often are you going to test positive if you do not have the disease? The bar over, remember, is not. So not having the disease is what we have here, the opposite of having it. If we don't have the disease, we're going to test positive 5% of the time. 0.05 is a probability, because that's a false alarm. You've got a positive result when you didn't actually have the disease. That means you should test negative, obviously, 95% of the time. The test should be correct. You don't have it, it tells you you don't have it. It confirms your non-having it case. What is 0.05 times 0.9? 0.045. And what is 0.9 times 0.95? 0.855. Now down to...
So you can see that for this sort of problem that we have stated here, we can see that the major case would be that since the majority do not have the disease, and since the majority of the cases who do not have the disease will have a negative result, of all the possible outcomes, actually joint probabilities, the most probable is the one that we just pointed out. Okay.
Rounding, obviously, these numbers should sum back up to 100%. And this line here should sum to 100. This tree should sum to 100. This tree here should sum to 100. Everyone that has the disease gets a test result, so 100% of them go one place or the other. Everyone that doesn't have it gets a result, and we've accounted for 100% of our population. So you can add these back to make sure I haven't messed up the mathematics. Another check. You can add all four and make sure we have 100%. Now to our two questions, and this is where it gets interesting.
So far, we have not solved the problem. We have actually prepared to solve the problem. Making these calculations in this decision tree is not really solving the question that we wanted to know. It is just preparation for the question. Now let's see the questions.
Just like in the previous probability slide where we limited our world to people that had the given condition, we now know you tested positive. That means you're either in this group or this group. What is the probability you have a disease? Let's get the whole world first. If you tested positive, you're either in this 0.045 or the other one, 0.092. Those are the...
So if you know your result, this is what we are doing. We know our observations, we know our results, we know what our model states. So we know our result. Now let's see what does this result state about the reality, the real world.
Groups that tested positive. It says, what's the probability you have the disease? Which of these two numbers means you had the disease? This one was from not having it. This one's from having it, so clearly 0.092. And our answer is 0.092 divided by 0.045 plus 0.092. Let's see what that gives us. Assuming I can type properly today, I get a probability of 67% or 0.67 rounded off.
So what has happened? If you tested positive, what is the according to the before your test, you were 10% likely to have it. After you tested positive, your 10% probability actually updated to a lot higher, because we know now that we have made test that shows us that you tested positive, and this test actually showed actually after this test we can calculate that your probability of having it is a lot higher, but still not 92%, right? And also, if we want to make sure, and this is why for example right now we are being vaccinated twice, if we want to make sure to increase this value really high, we need to make another test starting with this probability. We do another test, and if the other test comes up positive again, then this will update a lot higher. And I think it's going to update higher than the 92%, about 98%. I have to calculate this, but it's going to update a lot higher. So
sorry, after this first test, if I want to make a second test, I would replace my disease of 10% with this 67, right?
Exactly, because you're no longer the regular person who is average from the crowd, but you're part of the population where you have tested positive. Right? Okay. So the group of people will be smaller, but the percentage of them, so the probabilities for among this population will be, the new updated one. Okay. And of course, he is going to, the lecturer here is going to specify this as well.
So that's a lot worse than we might have thought. Initially, a lot of people will guess that it's 92% that you have the disease, since it's 92% accurate. But it is far lower than that. It's only 2/3 chance you have the disease, despite a 9 out of 10, better than 9 out of 10 original probability. If this was lower, it'd be even worse. Now your friend tested negative. What is the probability they have the disease? So we do the same type of logic. And maybe I'll put the answer up here, because I seem to be writing off the screen if I write below this line. So I have paper, but we don't have camera there, so I'll move up here. If you test negative, you're in the two negative classes, so 0.855.
So again, we construct the universe first of all the ones who have tested negative.
Plus 0.008. Negative and negative added together. Now what is the probability they have the disease? Which of these two numbers came from someone having the disease? Well, clearly have is up here, so it's 0.008. And we're going to get a remarkably unlikely event here. And I'm getting 0.009. So not even a 1 in 100, slightly lower than 1 in 100%. So 9 out of 1,000 people. Well, if you think about it, you were 90% likely to not have the disease before we knew anything. And now you have a test that's confirming you don't have the disease. So you're really, really unlikely to have it. In fact, the probability you don't have it would be 1 minus that, or 0.9907. So 99% of the time, if you've tested negative when you weren't likely to have it in the beginning, you're even less likely to have it now. If you've
so again, the probability of not having increased from 90% to 99%, updated in this sense.
Tested positive, you went from a 10% probability of having it before you took the test up to 67. So it's made it much more likely to have a disease, but not as likely as that number. Depending on the number, sometimes it can still be extremely unlikely to have a condition, even with a positive test. So I hope this has been instructive in how we can do practical Bayes calculations, and we don't really need the confusing Bayes formula.
Right? So, yes, this is one of the my advice. The Bayes formula is formulated a little hairy, more than I would like to, where it is a lot more simple principle. Although a lot of my colleagues who are specialists in Bayesian statistics would give you very sophisticated lectures here, which would have extremely interesting considerations, philosophy, and so on. So I have decided to let's make it a sort of a European type of a problem. So let's exercise with this one. So first of all, we have we are going to play the role here of a bookmaker, basically, or of a person who is interested in managing the risk of a main event by observing some additional aspects, tests, models, forecasts, you name it, about this main event or main phenomenon. So in this case, let's say the final of the Champions League. And by the way, it's my slide is a little older because I've been doing this problem for a long time. So you see this. Still, we have some probability. Okay, first of all, the two teams that are playing the Champions League are Barcelona and Real Madrid. Let's put it that way. There was, I think, at least on one occasion we had this final of the Champions League, I think. And why did I choose to be the final instead of just any game? Can you guess? Can you guess why?
Also I have a problem to read it, the slide. I can't read it.
Really? Okay. So in this case, let us stop our camera and do the same thing like yesterday with the. And actually, I am going to switch to my other internet.
Now it's good. Now I can read it.
Okay. All right. So
Daniel, I could read it without problems. Maybe it's on your connection.
All right. All right. Okay. So why have I chosen the Champions League final instead of just I don't know a game from the Premier League where we have Real Madrid and Barcelona, you know, the El Clásico. Why have I chose the final as an example here? Can you guess this one? Okay, you probably cannot. On any game of a regular season in between Barcelona and Real Madrid, there could be 3 outcomes.
Okay.
And this would make a little bit more complicated decision tree. And if it's the Champions League final, there is only going to be one winner at the end. It doesn't matter how we do it. I would like to apologize on the behalf of my son here. Right. So here are what are the probabilities as have been estimated before we know for the anything else. These are the so-called prior probabilities. So Real winning 45% of the time, Barcelona winning 55% of the time. And we also know that Ronaldo, let's suppose that he still plays for Real Madrid. He is not playing for Real Madrid for quite some time now, but anyways. Excuse me again.
Take your time.
Right. It's not. No. It's you know, he's going to be fat right now. So, right. Ronaldo scored in 80% of Real victories. So every time on 80%, 4 out of 5 Real victories, Ronaldo has scored. Well, it seems logical. Ronaldo seems like used to be one of their favorite best players. So if he scores, there is a good chance that Real Madrid would win, right? And Ronaldo has scored in 30% of all the other matches where Real didn't win. So this is what we have as an additional, let's say, test, an additional information. And we are observing the game as it goes. We are observing what happens on the field and trying to predict the final score. By the way, you probably know that the majority of the bookmakers are actually accepting bets during all the games. And at one moment, when they know that they have hedged the game, so they have a hedging, they close it. But anyways, the problem here first is let us make a decision tree, and after that we're going to answer these 2 questions. So question number 1, what is the probability of Real winning without the goal of Ronaldo? So imagine that all of a sudden before the beginning of the game, Ronaldo becomes injured and he cannot continue playing the game. So if we know this, obviously we need to update the probability of Real winning. Just an intuition. where would the winning percentage or winning probability of Real go? Higher or lower? If they don't have their best player.
Lower.
Yeah, obviously lower. So we'll see where, but it should go lower. This is sort of the sanity check. And what is the probability? The opposite question. What is the probability of Barcelona winning if Ronaldo scores a goal? So imagine the game starts, and on the second minute, Ronaldo scores a goal. So we are still at the beginning of the game. We already know that Ronaldo has scored the goal. So what would be the probability of Barcelona? Where will it go, by the way? Where it started 55%, where will it go if they have conceived a goal by Ronaldo? Upper or lower?
Sorry, Angel, can you repeat? I still.
Yes, I'm repeating. So I'm repeating. At the beginning of the game, before the start of the game, Barcelona's winning chances were 55%.
Yeah.
And in the second minute, the Real Madrid score goal by Ronaldo. Where does this? How does this changes the probability for Barcelona to win? Higher or lower?
Lower.
Lower, obviously, because even if it's not Ronaldo, they still conceive the goal. So it's they are at worse off position. Okay, yeah. So we're going to return to these questions later on. First of all, we will need to build our decision tree, and it would look something like this. So
I'm sorry, one question.
Yeah.
I'm not sure I got the second point. So we know that Ronaldo scored in 80%
of the victories. Yes, 80% of the victories of Real.
Okay, from all victories, Ronaldo. Okay, and what else is 30% about?
So Real Madrid has played, let's say, 50 games this season. Out of these 50 games, they have won 40 games.
Right.
And in 80% of these 40 games, which basically comes down to what is 80% of 40? 32. In 32 games of those 40%, Ronaldo has scored. This is the fact. In the other 10 games, which Real did not win, so a tie or a loss, Ronaldo scored in 3 out of 30%, so 3 out of 10, so in 3 games. Okay.
Yeah.
So out of the total games, some are with one type of outcome, which we are going to be interested. Some another are with another type of outcomes, and within these smaller universes, one outcomes or the other outcomes, we have these percentages. Okay, I think this is easier.
Yeah,
okay?
Got it. Thank you.
Okay, I would like to apologize that I have this. I have not seen that this is in Bulgarian, but it is Real Madrid.
It's not a problem. Daniel can read it.
Yeah.
No, this is Real wins. And this is Ronaldo scores. Okay?
I'm always surprised how you can translate the names into Cyrillic signs.
Okay. The same thing is when I go to Greece for me.
Yeah, okay.
Greek is a strange alphabet, and of course we've studied enough physics and mathematics to know all the alphabet. And actually, I'm very fluent in reading Greek. But I just, on most occasions, I do not know what it means, the hell. And you should know that some of the letters in Greek are actually the same in Cyrillic. Some of the letters are the same in Latin, and some are totally unknown. So, yes, I understand this. Anyhow. So, what we are observing at the end is whether Ronaldo scores, and what we're trying to predict is whether Real will win. This is what we have. This is our test. And this is our reality. And in this case, reality coincides with the name of Real. Okay, so first of all, let us construct the unconditional probabilities. Real wins yes, and Real wins no. Yes is 45%. Yes is 45%. This is how it's given. No is 55%, right? And there are no other outcomes. This is why we chosen the Champions League final. Okay. So if Real wins, we know the history for this of this event. We know that in the Real wins, Ronaldo scores 80% of the time, and obviously in the rest 20% he doesn't score. Okay. And out of the games that Real does not win, Ronaldo scores in 30% of the time, and in the rest 70% he doesn't score. Is this clear?
Yeah.
And if we calculate the joint probabilities, we are going to end up with four different situations. It is if Real wins and Ronaldo scores, this is going to be 36%. If Real wins and Ronaldo doesn't score, this is 9%. If Real doesn't win and Ronaldo still scores, this will be 16.5%. And if Real wins and Ronaldo does not score, this will be 38% of the time and 38.5% of the time. And obviously, these two things, these two values are the extreme values here, this one and this one. And you can have the same intuition. If Ronaldo wins, obviously there is a good chance that Real has won. And if Ronaldo doesn't score, there is a good chance that Real has not won. I mean, because at least there is one score less. Okay, this is our decision tree with its joint probabilities. Now we have to move, or we should move to answering the questions. So question number one, and we have to. I would like to remind you, we have to construct the whole universe in the denominator, and in the nominator we have to put the value which comes from the desired outcome. So what is the probability of Real winning? So this is the desired outcome, and we are looking at the situation where Ronaldo doesn't score. So I'm going to underline this twice. And first of all, the denominator, Ronaldo doesn't score. This is this one, so this number plus that number, right? It's going to be 47.5 in the denominator. And Real winning, which of these numbers come from Real winning? It is 9%. And if you calculate, actually, I have this. Why did I do this like this? I have this calculated already. Sorry for this. Okay, so 9% divided by the sum of all the occasions, and we have 18.95. So Real winning is at the beginning, unconditional probability is 45%. But if we know that Ronaldo has been injured and he's not going to score a goal, this has to be lowered, as we had this intuition already, and it goes down all the way down to almost 90%. So this almost, almost 1/3 of the probabilities is left over. Okay, and this makes sense, of course. So the second question: what is the probability of Barcelona winning? So basically means this part. If Ronaldo scores, so the desired condition is this one. This would be in the denominator, and Ronaldo scores a goal will be in the numerator. Again, I shouldn't have scratched this because I think I have this solved. Yes. So, oops. Yes, sorry. So we need to construct the Ronaldo score, which means that we take 16.5 plus 36. This will be our denominator, and the 16.5, because it comes from Barcelona winning, goes into the nominator. So something like this. And if we, calculate this, it comes down to 31.43%. And let's, again check, make a sanity check. So we have the Barcelona having winning at 55% at the beginning, unconstrained probabilities, but focusing or thinking on the situation a little bit more, finding out that Ronaldo scores in the first or the second minute. This means that the intuition that we have is that the Barcelona should lower their probability of winning, and the probability of winning actually lowers down to 31 and a half almost percent. So it's not half. They still have the chance to win, but it is significantly lower. And of course, we can observe many other factors. So we can have a condition for, let's say, what was the guy from Barcelona?
Lionel?
How did you call him?
Lionel Messi?
Yeah, Lionel Messi. Yeah. If we have another condition, how many the same weight? In how many of the victories Lionel Messi scores, and in how many of the non-victories of Barcelona Lionel Messi also scores? We could have these three expanded. Actually, it's going to be for each of these we'll have another two scores. Lionel Messi scores and not scores. And if we have another type of condition, this would branch again, and so on. And of course, sometimes the condition could be with three possible outcomes, right? And some case, by the way, if we have a prior condition that is equal to 0, we might not include this branch as well. So it could be okay. So, and we can grow these three, bigger and bigger. Of course, at one moment we are going to have to do this in a computerized manner instead of solving it by hand. But it is really going to be accounting for all specific conditions that have been changed since the beginning of the situation. So we have had some initial estimation, and after that we can add additional conditions or additional things that we observe. And if we know that one of them has happened or has already occurred, we can update all the other probabilities. And by the way, if we are to make this type of tree in this direction, we are going to put at the end the easiest ones to be tested, or the easiest one to be figured out, or to be found out, and the ones that are harder to figure out or to know will be to the left. But every time we know, we update our probabilities. And if at one moment, let's say if at one moment one of these probability actually is updated to, let's say, 98%, 98% then we might say, okay, there is no more need to make our analysis. Or it might be even less. We might not need to go all the way to 98%, or let's say 90%, and so on. Okay, so this is really an important idea. It is much bigger than the risk management. It is much bigger than probability theory. It is, namely, it is the principle behind every modern successful algorithm. You probably know that there are about, I don't know, 1,000, maybe not so much, maybe 100 of very important algorithms that keep the world afloat right now. Algorithm number one that we rely on is, of course, the Google search engine, and it is actually underlying is the same principle. We update our probabilities with all the observable conditions, and actually it depends on how many conditions we would like to observe. We can change this. Okay, now it's probably a good time to have a little bit of a break. So I propose let's make